Welcome to my online course in linear algebra for undergraduate mathematics. Today we are going to discuss singular and non-singular linear transformation. A linear transformation T from U to V is said to be non-singular if T image of x is equal to 0 implies x is 0 vector. A linear transformation T from U to V is said to be singular linear transformation if there exists non-zero vector such that their T image is equal to 0. Alternatively, a linear transformation T from P to W is called non-singular linear transformation if kernel of T is equal to 0, that is, if T is 1. Next is the theorem. A linear transformation T from V to W is non-singular if T carries its linearly independent subset of V onto linearly independent subset of W. First, let T be non-singular. We then consider S equal to B1, B2, P and be a linearly independent subset of B. We shall show that T of S is equal to T of B1, T of B2, T of Bm is also linearly independent. Let alpha 1, alpha 2, alpha n be scalar such that uh, linear combination of this scalar with this vector is my 0. In the next step, use the property of linear transformation. We can write this T of alpha 1 b1 up to T of alpha n bn is equal to 0. Again, by using the property of linear transformation, we can write this as T of alpha 1 b1 plus alpha n bn is equal to 0. This implies since this non-singular, T image of this element is equal to 0. This implies this element is 0 and this element is 0. Then since the set S equal to B1, B2, Bn is linearly independent subset of B. So these scalars are 0. This means Ts is also a linearly independent set. That is, this set T of B1, T of B2 up to T of Bn is linearly independent. Next, conversely, T carries his linearly independent subset of B into a linearly independent subset of W. We have to show that T is non-singular. Let B equal to U1, U2, Un be a basis of B. By a given condition, T of B equal to T of U1, T of U2, T of Un is linearly independent subset of W. Let x belongs to V such that T of x is equal to 0. We have considered let x belongs to V such that T of x is equal to 0. Then we are going to show that x is equal to 0. Since B is a basis of V, B equal to my this vector U1, U2, Un is a basis of V. So each x belongs to V can be uniquely expressed in terms of this basis element. That is x equal to alpha 1 u1 plus alpha 2 u2 plus alpha n un for some scalars alpha 1 alpha 2 alpha n. Now T of x is equal to 0. We have considered this one. Put this here, x equal to this linear combination. Here we will get T of alpha 1 u1 plus alpha 2 u2 plus alpha n un is equal to 0. By using the property of linear transformation, we will get alpha 1 t u1 plus alpha 2 t u2 plus alpha n t un is equal to 0 as t u2 t un is linearly independent. That is, this is the set T of B which is linearly independent. So this scalar are 0. Therefore this x is my 0. Hence T is my singular as all T map only 0 element to 0. So T is non-singular. Hence the theorem. Next is invertible linear transformation. A linear transformation T from V to W is invertible if and only if it is 1, 1 onto an inverse map is defined as T inverse is equal to W to V such that for all y belongs to W, T inverse of y is equal to x if and only if T of x is equal to y. Next, we shall show that T inverse is linear transformation. That is, we are going to show that T satisfied this condition. That is, T inverse alpha W1 plus beta W2 is equal to alpha T inverse W1 plus beta T inverse W2 for some alpha beta belongs to F, W1 W2 belongs to W. Since T is on 2 for any W1 W2 belongs to W, there exists B1 B2 belongs to V such that T of B1 is equal to W1 and T of B2 is equal to W2. As T is 1 1 and on 2, this implies the V1 is equal to T inverse W1 and B2 is equal to the T inverse W2. Now, T inverse of alpha W1 plus beta W2 is equal to T inverse alpha. Here W1 is my W1 is this one, T of B1, and W2 is T of B2. Put these values. W1 equal to alpha T of B1 plus beta T of B2. Then bring alpha inside and beta inside. I will get T of, in the next step, it is T inverse T of alpha B1 plus T of beta B2. This is equal to T inverse T of alpha B1 plus beta B2. T inverse is my identity map. Identity mapping of this element will give you the element vec. So this is alpha B1 plus beta B2. From here, I will get alpha in place of B1. I am putting this one. That is T inverse W1 plus beta T inverse W2. This theorem is your home assignment. You should try to solve this one. If you are unable to solve this, you should inform me. I will solve it for you. Remaining will be in the next lecture. With that, I would like to conclude. Thank you.